Vanakkam. Welcome to this video on biomechanics. We have been looking at viscoelasticity, that is biological materials exhibiting both viscous and elastic properties. In the last video, we looked at one model of viscoelasticity, which is the Maxwell model of viscoelasticity. In this video, we will continue our discussion on viscoelasticity, which is our time dependent deviation in elastic behavior, that is time or strain rate dependent changes in elastic behavior. In biological materials, or most biological materials are viscoelastic, so it makes sense for us to understand how viscoelasticity works. In this video, we will be looking at another model of viscoelasticity, and this model is called as Voight model. And as we did with the Maxwell model, we will be looking at creep and stress relaxation functions for the Voight model. This is the Voight model. This is a dashpot in parallel with the spring. Okay. In the Maxwell model, what we had was a dashpot in series with the spring. Here you have a dashpot in parallel with the spring, which means that there will be qualitative difference in the response of this model when compared with the Maxwell model. That makes sense, but we do not know what exactly that is. In other words, we have not yet done the mathematical formulation of this, which we will do. But just by examination of this model, I am looking at this model and I immediately know that the response is going to be qualitatively different. How? Because previously the force felt by the two elements in the Maxwell model was the same, but the deformations were different, and we summed the deformation to a total deformation, and then we modeled the whole thing as a function of the deformation, and then we converted it into forces and with appropriate initial conditions and so on. Remember, that is what we did. But in the Voight model, the force that will be felt by the two elements will be the same, but the deformations will not be the same. Okay, something to keep in mind. So immediately it becomes obvious that that the difference will be qualitative. So I can immediately think that there will be some difference. Okay. So this is the Voight model, in which the dashpot is in parallel with the spring. Remember, in the Maxwell model, we had the dashpot and the spring in series with each other. So the results and the response to applied stress or strain, or the applied force or deformation, will be different between the Maxwell model and the Voight model. Why? Because of the way in which I have formulated, because of the model itself. Because in the previous case, in the Maxwell model, these two were in series, now they are in parallel. So obviously there will be some behavioral difference between the two. Okay. The forces, when you pull this model on two sides, the deformation on both sides will be the same, but the force that is felt by each of these two elements will be different. What will be the force that will be felt at the dashpot? That is Fa, that is Cx dot. I can say Cx1 dot, but in this case x1, which is the deformation at the element 1, and the deformation at the element 2 is some x. Okay. So I can say that the force that is felt at the dashpot is Cx dot, and the force that is felt at the spring is some Fb, second element is some Fb, and that value is Kx. These are the two forces that will be felt. X is the same, x is the same. Okay. So the total force that is felt by the whole system F is a function of the two forces Fa and Fb, or I can say F1 plus F2 or something like that. Okay. So let's write this out. deformations x1 felt by element 1, which is the dash part, is equal to x2, which is a deformation felt by the spring second element, which is the spring, the same as sum x, okay, sum x. The forces F is the sum of the two individual forces F1 plus F2. We will call this, instead of Fa, I am going to call this F1, instead of Fb I am going to call this, sorry, instead of Fb I am going to call this F2, okay, because here I am using x1 x2, so it makes sense for me to use F1 F2, okay. What is F1? F1 is, but dx1 is dx, okay, that is C dx by dt or Cx dot plus F2 is Kx. I can say Kx2, but then x2 is x, okay. This is actually C x1 dot, but x1 is x, so that is essentially Cx dot or C dx by dt. F2 is Kx2, but then x2 is x, so that is Kx, okay. So this is C dx by dt plus Kx. So what would be the initial condition for this model? The deformation x of t at time t equal to 0 is 0, that is the deformation, that is the initial condition. The deformation x of time t equal to 0 is equal to 0, the deformation is 0, and this is true for any f, okay, for any f. Why is this the case? Because although the spring will immediately start to deform, the dash part as a whole prevents any immediate deformation, because dash part prevents instantaneous deformation, okay. All right. This is the initial condition. Okay. Now, if I apply a force, some force f of t is the theta of t, as we discussed in the Maxwell model, what would be x of t for this f of t? What would be the response? That would be f naught by k times 1 minus e power minus k by c times t, whole thing times theta of t, right. That is, if c by k, or if tau is equal to c by k, this would become 1 minus e power minus t by tau, right. The creep function, this is the creep function for an applied force, which is the Heaviside step function. If you have a step increase in force or stress, the deformation or strain increases exponentially, as in tau, where tau is c by k, because this is 1 minus e power minus t by tau, it is not e power minus t by tau. E power minus t by tau is a decreasing function. This is 1 minus e power minus t by tau, which is a which is an increasing function, right. So, that happens, and that is along expected lines, right, because that is what you would expect from a viscoelastic material, right, because this is the creep behavior. So, as time passes, the strain continues to increase for constant stress, that is creep, that is the behavior that you would expect in a viscoelastic material, and that depends on two things, right, that depends on, that is actually not a simple function of only one of these factors, that depends on both C and K, because tau is C by K, that depends on both the damping coefficient or the damping constant of the dashpot C and the spring constant K, both of these will play a role in this. Now, suppose the application, suppose I am applying, instead of a force I am applying a deformation x of t, okay. Suppose I am applying some x of t, which is actually this force that is applied is theta of t times f naught, is it not, theta of t times f naught, some initial force times, likewise x naught times theta of t if I am applying, right, that is the response. And suppose I apply the response is f of t is C x naught times delta of t plus k x naught times theta of t, is it not. So, how do I know all these things, how do I get this? From some basic analysis of differential equations, I request you to please revise this, right, because I know the initial conditions, I just have to substitute and redo some. So, if I understand this, then I can quickly write this as f of t is C x naught times delta of t, where what is delta of t? This is the direct delta function. So, what this means is that initially due to the dashpot there is going to be a sudden increase in the force as in the direct delta function, but then that immediately settles down, because as t increases, t is greater than 0, t is greater than capital T by 2 for example, then the direct delta function does not exist anymore, the whole thing becomes 0, then you only have the response due to the spring, which is k x naught times theta of t, which is a step change in the spring, only the spring response remains. So, initially there will be a sudden increase in force and then that will decrease and then become the step function according to the applied deformation. This is the expected stress or force, okay. Of course, you can, I request you to please check this by substitution, check this mathematics by substitution whether these formulations are correct. They are correct, but please do check for your own understanding, okay. So, what are the predictions and what are the results from the Voight model? In the creep experiments, initially there is an exponential increase in creep, as in 1 minus e power minus t by tau. Where do I know have this? That is this, is it not? 1 minus e power minus t by tau. Why is this happening? Due to the dashpot. Due to the dashpot, I am having this, increase or a response in which the deformation is increased as time passes, okay, where tau is C by K. Okay. Now, when the force is removed, what happens? This initial force is removed, then this force decays as in e power minus t by tau. This is also decaying, but this is a decreasing function, because this is 1 minus e power minus t by tau. By the way, by now we must be in a position to identify which is e power minus t by tau and which is 1 minus e power minus t by tau by just looking, right. because this is exponentially decaying. Compare this with the creep results of the Maxwell model, and you will realize that there is a qualitative difference in creep between the Maxwell model and the Voight model, right. There is a qualitative difference between the predictions of the Maxwell model and the Voight model. Okay. On the one hand, the creep function prediction by one seems to be more accurate or more acceptable or more realistic than the other. So, it seems like both of these models are able to account for specific things, but are they the full story is something that we will have to wait and watch. Okay. So, this is the creep result. So, as I am increasing the force, the response, the deformation increases as in 1 minus e power minus t by tau, and if I remove the force, it decays as in e power minus t by tau. Okay. If I perform a stress relaxation experiment, what happens? Stress relaxation experiment is, if I apply a step change in deformation or strain, what happens to the force or stress? That is the question. Well, if I apply a step change in strain, there will be a direct delta function in force, but that will last only a very brief period, right, because direct delta function is going to last for a very small amount of time, which is capital T divided by 2, where capital T itself is a very small amount of time. So, it is a really small amount of time. So, at that time there is going to be a sudden increase in stress or force, a very large increase perhaps, an immediate and sudden but temporary, an immediate, abrupt, sudden, whatever, sudden, large increase, but temporary change due to the direct delta function. This is seen in the force, this is due to the dashpot alone, as seen in the dashpot alone, and then as time passes, very quickly the force settles down into the force that would be produced by the spring alone at this level. Once again, this is also qualitatively different from the predictions of the Maxwell model, is it not? Well, one challenge with this model is, what is the meaning, physical meaning of this direct delta function, delta of t? Physically, is this realizable, this function, is this realizable? An extremely large amount of force in an extremely small amount of time is physically not realizable. So, this is a drawback or a challenge with the Voight model, something to keep in mind, that, that this model gives out a response that requires a very large amount of force to be produced in an extremely small amount of time, which is not physically realizable. Okay. So, there are both disadvantages or some limitations to these two models, Maxwell model and Voight model. So, in this video we looked at another model of viscoelasticity, the Voight model, and we discussed the creep function and the stress relaxation function using the Voight model. With this, we come to the end of this video. Thank you very much for your attention.